So far in our electron configurations, we have always started at the very beginning. According to the Aufbau principle, you always fill the lowest energy level ones first, and then you add electrons. So you start with 1s, go to 2s, and then 2p, and then 3s, etc. Okay, a lot of times though, the electrons that we care about, if you think about an atom's got the nucleus here, and then you've got some electrons here, and those are supposed to be electrons. Then some here, and then some out here. And as you start having more and more electrons, if you think about it, when atoms are involved in a chemical reaction, which are the electrons that are going to be most affected? Are those ones that are out in that outer and kind of in that outer region? Okay, the ones that are the farthest ones from the nucleus. Okay. And that's where what are called the valence electrons come in. Is the valence electrons are the electrons that are in the last shell of the atom. So remember in our last video when we talked about like 4s2, 3d10, 4p5, when you took electrons away, remember we learned that you always take them away from the furthest shell first. So those electrons get taken away first, and then those electrons would get taken away. Okay, those electrons right there that are in the fourth shell in this case, those are called the valence electrons. Okay, and so the last shell, the very last shell, that might just involve electrons in the s subshell, but might also include the s and the p subshell, those are the valence electrons. Okay, and we're going to see some more of that here in just a minute. Okay, so the very last shell, the electrons that are in the last shell, those are the valence electrons. And the reason that we care about those is because, again, when chemical reactions happen, those are the electrons that get affected, that are changed, are those ones that are the farthest ones from the nucleus. Okay, so when we look at, for example, carbon, okay, carbon's electron configuration is 1s2, 2s2. So that means there's 2 electrons in the 1s subshell, so that's the first shell. And then in the second shell, we have the 2s and the 2p. Okay, so what are the valence electrons? These are the valence electrons. Okay, and how do I know that? Because the last shell is the second shell, and there's 2 electrons in the s subshell, and there's 2 electrons in the p subshell based on these numbers right here. So therefore, we could say that carbon has 4 valence electrons. Like I said, 2 in the 2s subshell, 2 in the 2p subshell. More importantly, 4 all total in the second shell. Okay? Now, a lot of times, how am I supposed to know how many valence electrons an atom has? Typically, you can simply use the periodic table. Okay? So looking at a periodic table, if you think about it, every single element that's in this very first column here ends in 1s1 or 2s1 or 3s1 or 4s1, etc. They all end in s1. That means that every single atom in that first column has 1 valence electron. And then when we jump over to the next column right here, all of those have 2 valence electrons. Now why? Well, think about their electron configurations. They all end in 1s2, 2s2, 3s2, 4s2, 5s2, right? So they all have just the 2 valence electrons. Now, we skip the d subshell, and again, why do we do that? Because we know the d subshell is 1 behind the s's and the p's. So in terms of valence electrons, we now just continue. There's 3, 4, 5, 6, 7, and 8. Okay, so an atom can have a maximum of 8 valence electrons, not any more than that. Okay, and how do you know? You simply look at, selenium is right here on the periodic table. How many does it have? Oh, it has 6 valence electrons. Oh, aluminum's right here. How many valence electrons does it have? Oh, it has 3. So whatever column it is, up from 1 to 8, that's the number of valence electrons that atom has. Okay, so it explains right here. An easy way to determine the number of valence electrons in an atom is to look at the periodic table, count from the left to the right, from 1 to 8, And that's how you know how many valence electrons. So I should be able to point at any element in the S or the P subshells and ask you how many valence electrons they have. And you should be able to simply look at the periodic table and tell me what that is. Okay? Now, a lot of times the reason that we care about this is because, again, these are the electrons that are involved in chemical reactions. So a lot of times when we write the electron configuration, we write what's called the valence shell electron configuration, which just means you write the electron configuration, but you only show the valence electrons. Okay, so here's an example of this. Write the electron configuration of selenium, but only show the valence electrons. So, again, to start this out, sometimes it's helpful to write out the whole thing. So here's normal old selenium, 1s2 all the way up to 4p4. Okay, and then we look and we say, okay, which electrons are in the last shell? Well, here's the first shell. Here's the second shell. Here's the third shell. And then right here and right here, that is the fourth shell. That is the last shell. Those are the valence electrons. Notice that there's 2 plus 4. Look at selenium on the periodic table. You should notice that selenium does have 6 valence electrons based on that 1 to 8 thing. Okay, and so the valence shell electron configuration of selenium, as you can see right there, is just 4s2, 4p4. Oh, so it's basically the same thing we've been doing. It's just a shorter version of it. Yes, exactly. That's exactly what this is. Okay, example 2, write the valence shell electron configuration of strontium. So strontium, again, if you think about the whole thing, strontium actually looks pretty similar coming back up here to selenium. It just keeps going. It's 4p6 and then it goes 5s2. Okay, so with strontium, using this as our example, what's the furthest shell from the nucleus? Well, not the fourth shell anymore, because now we have electrons in the fifth shell. So those are our valence electrons. Okay, and so the valence shell electron configuration of strontium is just 5s2. Okay, so remember, it's the electrons in the last S, and if they're there, P subshell, that have the same number here as the S one does. Okay, and you don't include the D subshell. You certainly don't include the F subshell when you're doing these. Okay, so example 3, write the electron configuration of the following atoms or ions, only showing the valence electrons. So the first thing we have to do is we have to find these elements on the periodic table. So tin is number 50, and it is in the 5th row down, 1, 2, 3, 4, 5. So tin, again, the ending should be 5s2, 4d10, 5p2, but remember, we don't include that D subshell when we're writing the valence electrons. So it's just going to be 5s2 and then 5p also 2. 1, 2, 3, yep, the 5th period, okay? Okay, Si2 minus. So now we have an element that has a charge. So again, regular silicon would be 1s2, 2s2, 2p6, 3s2, 3p2. But with a -2 charge, it's going to be 3p4, right? With a -2, you add 2 electrons. So again, regular silicon, 1s2, 2s2, 2p6, 3s2, 3p2. But then with the -2 charge, it becomes 3p4. And then if we're only showing the valence electrons, well, what's our last shell? It's right here. So it's just 3s2, 3p4. So yes, you can do this with ions as well. Okay, astatine, number 85. Oh, that goes down into the F subshell. It would if you were not showing the valence electrons, but I'm never going to make you do that. So astatine number 85 is in the 1, 2, 3, 4, 5. It's in the 6th period. So that's just going to be 6s2 and then 6p. And then it's in the almost the last column right next to the noble gases. So 6s2, 6p5. Okay, and then barium is actually in that same column. 6s2 is all that would be. And then our last one, element 119, is like, wait a minute, that's not even on the periodic table. You're right. But where would it be if it were on the periodic table? Is you just keep counting. So as you go across the bottom there, you do get to element 118, which is right below number 86. And so where would you go after that? Well, where do you go after element number 86? Well, you go to element number 87, which is, obviously you can see it on the left-hand side of the periodic table there. So where would element 119 go? It'd go right underneath element number 87. So that would be the 8th period. So that would just be the electron configuration would just be 8s1. And that's it. So you could even do this for elements that don't even exist. Okay, and then our last part here is what are called excited state electron configuration. And if I remember correctly, I did make a big mistake here. So I want to make sure that I fix that. Hopefully you're watching this video so you'll see my mistake. Okay, so when you write an electron configuration, we always write what's called the ground state electron configuration, which means you start at 1s2, then you go to 2s2, then you go to 2p6, 3s2, 3p6, etc. You always go with the lowest energy level first, and then you go from there. Okay, but a lot of times when you add energy to an atom, those electrons can move around. Okay, most of the street lights that we use here in the Tri-Cities use what's called sodium vapor. Okay, and the reason they use sodium is because when you excite a sodium atom and those electrons start to move around, it produces light. And that light that it produces is a yellowish color. And it doesn't take very much electricity to do it, so it's very energy efficient. And it does produce a nice yellow light. So at night when you're driving, or you're close to an intersection or something, you can see that yellow light being produced from the light. Okay, so or from those atoms. So what happens is like, for example, sodium is 1s2, 2s2, 2p6, 3s1. Okay, and what happens is when you excite that atom, this electron here, this 3s electron, can move up to a higher energy level. Okay, so an excited state electron configuration is one where one or more of the electrons are in a higher than normal energy level. So, again, I want you to completely forget about this example because it's wrong. So, with sodium, it normally is 1s2, 2s2, 2p6, 3s1. So if we're asked to write one possible excited state electron configuration for sodium, what that means is instead of 1s2, 2s2, 2p6, 3s1, we're going to take that electron and we're just going to move it to a higher energy level. It doesn't even matter which one, but notice, so that's why it says one possible excited state, because you can move that electron to a higher energy level. So instead of 3s1, again, just something higher than 3s. Could it just be 3p? Sure, it could be. 3p1 would be fine. Okay, could it be 6f1? Sure, anything higher than 3s. Now you'll notice the mistake I made here. Basically, instead of sodium, this would be magnesium. Okay, magnesium, normally 1s2, 2s2, 2p6, 3s2, but notice this one electron here got moved up to a higher energy level instead of being in the 3s subshell. So notice that instead of, again, not sodium, magnesium ending with 3s2, those electrons got moved up to a higher energy level. Now, once it gets to this higher energy level, let's say on sodium, that's very unstable. It's way, way higher than it's supposed to be. So what happens is it falls back down. It comes back to the ground state. And when it does that, when it falls back down, that's when it releases the energy. And that's when, in many cases, you see different colors produced from these elements. Okay? So let's look at a couple of examples here. Selenium. So again, I'm going to start with regular selenium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, oops, not p, 4s2, 3d10, 4p, 1, 2, 3, 4. So that's normal selenium. Okay. Now I want to make it an excited state. So that's the ground state electron configuration there. So I'm just going to take, well, I'm going to take 2 this time. I'm going to go 4p2, and then I'm going to go 5s1. How am I doing this? I'm just making this up, guys. And then we're going to go 6p1. So I took 2 of the electrons that are normally there, and I moved them both into just a higher energy state. Okay. Now, could I have put them both in 5s and made it 5s2? Sure. Could I have put them both in 6p and made it 6p2? Sure, it doesn't matter. Okay? What matters is you move 1 or more electrons from the ground state up to a higher energy state. Okay? Oxygen, 1s2, 2s2, 2p4 is normal oxygen. So this time I'm just going to move 1 electron, 2p3, and then 3p1. Okay? And how did I come up with 3p? I just made it up. Okay, I just thought I need something higher than 2p, so I could have gone to 3s, 3p, 4s, 3d, anything above the 2p. And then with magnesium, again, 1s2, 2s2, 2p6, 3s2 is normal magnesium. Take one of those. Let's take both of those away. Let's no 3s at all, and let's go 4p2. That would be fine. Clearly, it's not in the ground state. Could I go 4p1, 6s1? Sure. Just so, again, all 12 of those electrons are accounted for. Notice, add up those numbers in the corner. You just have to account for all 12 of them. Okay, and that is how you do excited state electron configurations.